que te convierte lo avanzado y nadie se pasa de Chile. Claro, se le puede decir que Miguel Coloma Puga.
Miguel Coloma. Miguel Coloma is here. Okay, sir.
Okay, good morning, everybody. Welcome to the last session, the last session of the AGN redemption meeting. Everybody's very excited, but we have to start. And welcome Rodrigo Nemmen, who's going to talk about JS and AGN's current progress. Thank you.
Thank you. So, microphone, yes. Hi. So I had the challenge of presenting a review about all jets in supermassive black holes, and because I think that most of the audience is graduate students, or a considerable fraction of the audience is graduate students, I wanted to begin with the suggested reading. Okay, so if you want to learn more about the subject, you can start with this beautiful annual review by Roger Blanford. And as you will see, Blanford will be a recurring name in this presentation. And if you want to learn even more, yeah, no, thank you. And if you want to learn more in depth about physics and phenomenology of jets, you can look at this. There are many books. So I suggest these 3 particular books. The first one has everything, observations and theory. The second also has everything. And the third is really like a hardcore theory book. And I only recommend if you really want to cross the internet. So let me begin by saying why jets are important. So jets are important for a variety of reasons. So they are incredible laboratories for high energy astrophysics, for understanding particle acceleration. Because jets are really by definition beams, they get very high luminosities. So you can see them in all sorts of redshifts. And so they are cosmological messengers. This is particularly true for galaxies, which are not supermassive. They are sources not only of electromagnetic radiation. This talk, by the way, will focus on electromagnetic radiation for obvious reasons, for selection effect of the audience. But they are sources of cosmic rays, they are sources of neutrinos, so they are really fantastic for multi-messenger astronomy. And finally, they potentially impact our scale structure through the so-called rate of feedback. So there are many reasons why jets are fascinating. But there is also another reason why jets are fascinating, specifically for supermassive black holes. Because in order to understand jet formation and evolution, you really need a huge scale, like a huge dynamic range, a huge difference between the smallest scale of the problem and the largest scale of the problem. So on the larger scales, you have the intergalactic MUSE, where I'm showing there jets blowing bubbles in the environment of a galactic galaxy cluster. Then we get down to the bony radius, which is more or less the sphere of gravitational influence of the black hole. Then we get down to horizon scales, and then there I'm showing the inner stable circular orbit, which is really the region where the action is happening for forming an AGN jet. And then finally, we'll have the smallest scale relevant from the point of view of plasma physics, which is the larger radius of electrons. Okay, so you really need all of these scales to really understand jet formation and evolution. And I think it becomes clear then that this is a very broad topic, very challenging to review this topic. And my review will be biased. I am disclaimer, this is biased, okay? I'm not trying to hide it. If I had 1 year, I would love, if my talk had 1 year, a continuous 1 year giving a talk, I would love to review all these topics of the events. But since I have 35 minutes, I will focus on formation, dynamics, and a few words about the status of the radio wide debate. In other words, why do only 10% of our supermassive black holes like to produce jets? I have a few ideas about the subject. Okay, and if I miss your favorite paper on the topic, sorry, not sorry, but I will be delighted to hear about it in the discussion. So let's begin with a recipe for generic jet formation. How do you get jets? How do you get a jet in general in the universe? So you need 3 ingredients to produce a jet. You need a colloidal large-scale magnetic field line, number 1. Number 2, you need accretion. You need to bring the field. You need to bring the field close to the center. And number 3, you need rotation. You need to create some sort of rotating structure. And if you have these 3 ingredients, you will get jets. I can promise you all of your jets, and that's why you see jets in protostellar objects. That's why we see jets from neutron stars. That's why we see jets in all sorts of black holes. But when we come to supermassive black holes, we use nowadays we converge a specific version of this generic recipe, which goes by the name of Planck's magic model. So the basic idea behind the Planck's magic model is that the jet is launched by magnetic fields that are twisted by the black hole speed. And I will show you a vintage, no, not so vintage, well, for most of this audience, this simulation is vintage from more than 20 years ago. This is a beautiful numerical experiment showing how the Planck's magic model works. So here, let's begin with a colloidal magnetic field line. And what will happen here is that I will let the field line be dragged by the spacetime. So what happens here, the field line that's dragged starts experiencing frame drag in the rotating spacetime of the black hole, and the field line gets spun around the black hole many times in the event horizon. And this gray region, which we can barely see here, is the thermosphere of the black hole. Okay? So eventually the toroidal pressure of the field line, because the magnetic field lines, they have tension. They have pressure, they have tension. So the toroidal pressure starts accumulating and makes the field line want to go away along the ejected along the poles of the curved black hole. By the way, the rotation, the angular momentum of the curved black hole is in this direction here. So for this reason, what happens is that basically the field line is ejected along the poles of the curved black hole. And as the field line is ejected, it will carry along any charges that are rotating in the field line. And this is the jet. Okay, this is the idea behind the Planck's magic model. Okay. It may sound fancy, but it's not. It's not a fancy idea. In fact, if you want to make a black hole jet at home, you can do it. Okay? And I highly recommend it. And you will not destroy your home, you will not destroy your hometown if you do this. Because the physics, so the physics behind the whole polar generator, which is also known as Faraday wheel, is the same basic physics behind the Leftley model. Okay? So the idea of a Faraday wheel is if you take a conductor, you spin the conductor and you put a magnetic field through the conductor. So if you do this, if you spin this conductor or a magnet, you can do this with a magnet as well. You can get current with power. Okay? So the blend force natural idea is really replacing this conductor with a rotating event horizon, which surprisingly behaves as a conductor. Okay? So this is the idea that Roger explored in the 70s, and this idea has been really explored to a dramatic degree. And when you put all of this together in this industry of general relativistic magnetic simulations, try to say that really fast. You get this, there is a whole industry of simulating accretion flows onto curved black holes and the associated jet formation. This is one simulation carried out by my graduate student, really talented graduate student, Pedro Mota. Where you have all the ingredients here. You have the accretion disk, you have wings, you have a jet, and of course the black hole. So this really became an industry after the observations of the two black hole shadows in 1997 Sagittarius A star, to the degree that we now have more than 7 codes for doing GRMHD, depending on whether you want to use the GPUs that you used to use for Bitcoin mining. And if you want to do that for simulating black holes, you can do that. So really, this really became an industry. So back to the blend force natural model. There is a really simple scaling for the jet power in this model. And the scaling is you can work on, you can actually do a back of the envelope calculations for arriving at this scaling. And basically, the jet power is proportional to the square of the dimensions, black hole speed times the magnetic flux threading the event horizon. Okay, so this is a really crucial prediction for such a model. And so, does this work? I mean, can we observationally probe this model? Is this model observationally correct? So I will devote a few minutes now discussing the observational evidence for this idea, the idea of the electromagnetic generation of jets in AGNs. So what is the challenge if you want to probe the BZ model observationally? So there are 3 key predictions of the BZ model. And that spoiler, I'm already grading them according to their the observational gradient to each of these tenets of the BZ model. Number 1, you need a dynamically important magnetic field close to the black hole on the scale I'm showing within a few gravitational waves. Number 2, you need a colloidal field. And number 3, you need reasonably large black hole spins. Okay? So let's talk about the evidence for each of these 3 requirements of the blend force natural scenario. So let's start with the first one. There is this beautiful result from a few years ago where these authors they came up with this clever way of estimating the magnetic flux. So the idea is they use the core shift technique to estimate the magnetic flux at parsec scales with the alpine observations. And then because of flux freezing or flux conservation, the flux should be the same down to the event horizon. So they estimated the magnetic flux on parsec scales. And so here what we are seeing is a plot showing the magnetic flux on parsec scales in the jet, estimated with VLBI observations, versus basically the accretion disk luminosity estimated with our broad emission lines, using these broad HB scalings among other scales. And what you're seeing here is that the magnetic flux times the accretion luminosity follows this time correlation. And in red, we were seeing the prediction of very specific, basically, the fact that this time correlation follows this red line means that the field is dynamically important close to the black. And if you are wondering what is MAT, don't worry, I will tell you what MAT is. I will get there very soon. So this result will be already showing us that the field is really important. Then we have this specific, you will see a lot of MUSE in this presentation, okay? This is another very fascinating result by Zihuagn's group in Shanghai. So what Fang and Palafox did here, they got the rotation measure, which is basically the commutative effect of magnetized plasma rotating the polarization angle. Okay? And so here what you are seeing is a comparison between the measured rotation measure rotation. The rotation measure for M87 and then comparing with two different models. The green model in the left plot is a model where the field is weak, close to the black hole. And the orange, I guess you can see it's orange if you're not daltonic. The orange is really a model where there are definitely important fields close to the black hole. So M87 rotation measure is already also favoring a scenario where the field is very strong close to the black hole. And I'm also in a paper from a couple of years ago, I already ruled the weak fields close to the black hole, particularly for M87 based on rotation measures and the measured average jet power for M87 on the right plot. What is a MAT? So we saw this acronym, MAT. So what is MAT? So MAT is a flavor, is a different view on standard accretion. So what is a MAT? MAT is a magnetically arrested disk, and MAT is the kind of flow you get when you flood the black hole with magnetic fields. So if you flood the black hole with magnetic fields over time, what happens is that so this is a standard accretion disk, and this is a MAT. Okay, SANE stands for standard evolution. As far as I know, this acronym is coined by the International Audience, SANE. MAT, I think Ramesh also coined MAT, if I'm not mistaken. So if you flood the black hole with magnetic field, with magnetic flux will accumulate in the region, and eventually the field will be so strong that it will overcome gravity. And so it will basically prevent accretion from happening. It will destroy the inner region of the accretion. So there are very strong amigos here. This is the idea of the magnet. And MAT is interesting for jet formation because if you get conditions for a MAT, you maximize the power that you can extract from the black hole. So you maximize jet power if you form a MAT around a pure black hole. Okay, so this is we'll see MAT more time in this presentation. And so we have evidence that whenever you have a jet, you have a black hole in the MAT state. Okay? It could be a hot riot in the outer parts, it could be a Venus, okay, but you have a strong, large magnetic flux close to the black hole. Now let's talk about the second tenet of the BZ model, which is the colloidal field. There is recently exciting evidence for M87, where, so what we are seeing here, we are seeing the polarized images of M87. On the left side, we are seeing the line revolution of the polarized image, the polarized the polarized observation. In the middle panel, we are seeing two different predictions for this magnetic field polarized scales. This is a comparison of what happens if the field is mostly toroidal, or what happens if the field is mostly colloidal. And interestingly enough, the polarization of M87 shown here is better in a situation where the field is mostly colloidal, which is again what you need to electromagnetic directly power jet in AGNs. So there is support for colloidal fields on horizon scales. Now let's talk about the most contentious aspect of the BC prediction, which is spin. You mean spin. What's the status of spin measurements for radio AGNs? And, well, I don't bring good news. So there is this idea called spin paradigm for AGN jets. And I think this theory is very robust. There's became a whole industry of those simulations. But in order to actually prove this idea of this spin paradigm, you actually need good spin measurements for radio AGNs. Do we have them? Let me first talk about the situation for stellar mass black holes, which in some cases are much better studied than an AGN with its million-year time scales for everything or even longer. For stellar mass black hole, you can see all the action happening in a couple of days or weeks. And for stellar mass black holes that produce jets, there is this fascinating result where these authors again, Ramesh, and Jeff Clinton and Jack Steiner, they published this plot, which is basically plotting the black hole spin measured with the spectroscopy for stellar mass black holes versus a proxy of the Jack model. And this is where it gets really tricky because this proxy is debated. So they found a scaling which is roughly the scaling expected from BC jets in stellar mass black holes. The thing is, this correlation, if you can call it that, this correlation is highly controversial. It's highly contentious. And the thing is, if you go to stellar mass black holes in the hard state, this correlation disappears. Okay, so this is still highly controversial, but at least there is some support for the BC model in stellar mass black holes. But when you go to AGNs, let me show you here a landscape of all the spin and the black hole spins measured with X-ray spectroscopy. The y-axis is the black hole spin, the x-axis is the mass. And we can immediately see in this plot that most of the measured spins from Earth spectroscopy, they cluster in high spin values. And again, the maximum spin is 1 for a appropriate situation. So we are seeing a clustering of black hole spins here, but look, these are all radio-wide AGNs. There's not a single reliable spin for a radio AGN. And the question is, according to the BC model, should this be radio-wide? Or should these large black hole spins here produce big girls, pretty jets in this object? Okay? So this is really teaching us that spin is not the only answer to powering jets. And spin seems to be a necessary but not sufficient condition for getting one of these beautiful jets to see F1s or F2 galaxies, okay? Yeah, galaxies. So the idea here, what I believe is happening is that you need magnetic flux. The missing piece of the puzzle is magnetic flux, the dipole magnetic flux. And this is a plot that I drew this plot for this presentation actually when I was thinking about the problem. And I believe that the radio population is in these two corners of this family, this plot, okay, where you have large magnetic fluxes and you have also large black hole spins. And this is possibly why only 10% of floating AGNs, only 10% show jets, because 10% are the object right in the corners of this parameter space. And this is part of the BC model, okay? Because remember, it depends on magnetic flux and spin. So let me say a few words about jet dynamics. So let me say a few words about collimation. So since 20 years ago, when the first GR simulations started being produced, we already knew that jets, when they come from black holes in the BC scenario, they already emerge collimated. on the horizon scale, so really from simulations which is automated, and they produce this structure which is called the spine sheath structure. Okay? So the idea here is that you have a pointing flux dominated spine, basically almost evacuated, and then you have a fast spine and a slower sheath, which is matter dominated, and you also have a matter wing. And the wing actually is not launched by the spin of the black hole, by the process happening in the accretion. And this prediction is being validated by observations of lane brightening in jazz with the LBI. So we have rotation measured gradients. You observe lane brightening in many jazz. But again, I will now say about I will show you not so recent result for M87. So again, M87, I cannot really contain myself. I have to show you this landscape of our observation. It's a really beautiful. We are living in the golden age of AGNs from we can image the horizon, we can see all the structures up to megaparsec scales. So here we begin with the halo, the radio halo at kiloparsec scales, and then we go down, we zooming. What I want to focus here is this observation here, which is showing lane brightening in the jet, which looks like the jet sheet predicted from geometry simulations. And we see this for all other regular AGN as well, when we have the resolution power with the image from close to horizon scale, the base of the jet. And by the way, this is an exciting result that was published 2 years ago. Again, this is giving us clues about jet collimation. So you all know, and perhaps love or not love, the EHT ring that was observed 6 years ago. Okay? It was announced 6 years ago, but there is now a second ring that was observed 2 years ago in a slightly longer wavelength, and that's what I'm showing you at the left side. So EHT constrained a second EM87 ring, and this is what we are learning here is that this ring is slightly larger than what you would expect from a BC jet launching, and this is probably telling us that there are some absorption effects due to a wind on the horizon scales, which is collimating the jet. Because the jet maintains collimation in its form because there is a wind collimating on the horizon scales. And actually, this is supporting this idea that there is this wind collimating the jet in its form. The second ring is roughly 3 times larger than the first ring, which is due to photons escaping from photon speed around the black hole. Okay, so when we put together these results for the jets, where we see that where we observe the collimation of the jet from horizon scales to beyond the volume range, we are getting this picture where the jets, they emerge from the black hole already structure, they continue collimating through many mechanisms. Vast scales. They have very complex topologies as they propagate. They are battling various instabilities as they propagate outwards. And here I'm comparing this scenario for M87. This is a very famous result by Azana, where you see the collimation, how the collimation of the M87 jet evolves with distance. And we see that there is a break at around the volume radius where the jet transitions from parabolic to conical. And the same thing was observed for the 3C273 jet, where it is parabolic and switches to conical at a different distance, which is roughly the volume radius for 3C273. And we believe the transition is because the jet transitions to an external pressure profile, a different pressure profile, which changes the confinement of the jet. So let me switch gears now dramatically because I wanted to spice up the talk with some theory results. So as I showed you, there is a vast range of scales here, and so there is a vigorous progress happening in jet theory. Many different aspects of theory are being debated. And again, I don't have time to talk about all of this, so I will try to cover in 5-ish minutes these specific topics here. So the first thing I wanted to talk about jet theory in this review talk is that you may not know, but the problem of the origin of radiology is much deeper than one could naively think. Because GRMHD models, they assume the black hole is surrounded by plasma. Okay? But that's not guaranteed, okay? So this is not obvious, okay? It's not obvious that close to the black hole, especially at the funnels of the jet, is populated by plasma. And you need that plasma to enforce the MHD conditions or the force-free condition. Okay? So kinetic simulations, which are basically, we can think of microscopic simulations of the plasma process. They ask, where does this plasma that populates the funnel of the jet, where does this plasma come from? And there is a lot of stake, there's a lot at stake here, because if there is not enough plasma in the jet funnel, the jet doesn't form at all. The jet gets switched off. Because you don't have the force-free conditions, and the magnetosphere stops rotating. You don't get a easy jet anymore. So what I'm showing you now is one particular kinetic simulation of this process. And so now the first full general relativity particle in cell simulation was produced 6 years ago by Carl Barfring and Sasha Filipov and others. And so what I'm showing you here is that they are basically evolving specific particles and evolving the Lorentz force in specific particles. And so there is a lot happening here, okay? This is really what's happening here is basically magic. No, I'm kidding, it's not magic. There's a lot of complicated plasma physics. But basically, let me restart the movie. It starts with well, it starts with vacuum from the black hole, with a magnetic topology that doesn't give you jets, and then pairs are produced around the black hole. They replenish the magnetosphere with plasma, and then in the end, we get something that looks like a busy jet, self-consistently, or more or less self-consistently, but also something quite intriguing, which is the Penrose process that you might have heard about, which is another way of extracting energy from rotating black holes. So this is really exciting theory progress. Another front of progress is tilted boosts. So on the left side, we were seeing the standard idea that 99.9% of theories they assume this is changing. But in the past, people just assume that the black hole speed is aligned with the accretion angular momentum, and that's that's how it goes. But the galaxy doesn't care. Okay? The gas flows in the galaxy doesn't care about the black hole angular momentum. And so this is an open question: what happens to the resulting wave in jet when you get a tilted disk? So there's a lot of progress in this field in the last 5 years. I will show you one specific simulation by Matthew Wisk and collaborators, and Matthew Wisk in Georgia. Matthew Wisk in Georgia Tech. So what you are seeing here is what happens when you misalign this with respect to the black hole. This is very complicated. But what's happening here, you get a wobbly jet which is processing, gets destroyed. The jet destroys the disk, but also the disk tears up because of the bargaining tears we found. And this was not possible 3 years ago because we didn't really have GRMHD focus, okay? And this has a lot of consequences for the regular long-range point paradigm, variability, understanding variability in AGNs, understanding changing look AGNs. We have evidence for processing jets, lots of different fronts of evidence that I will show you here, the evidence from 1987. where there is evidence for a persistent jet with a period of about 11 years. We have evidence for persistent jets from light curves. We saw a talk yesterday, or no, I forget it was whether it was Wednesday or Thursday. We have evidence for persistent jets from turbulent line curves, where we see potentially QPOs in the line curve. Now, there is a word of warning specifically about Fermi line curves, and I'm sure Luis is having a great time editing papers claiming QPOs in line curves and submit to APJ. You should not believe all these QPO allegations in Fermi line curves because of red noise. Some authors are interpreting red noise as QPOs, and I think my time is over. Well, you can ask me about bridging from the horizon to beyond the boundary radius. There are now simulations that simulate from the horizon to beyond the boundary radius in geometry. This is really fascinating progress. I want to give a shout out to my former graduate student, Zihuagn, currently at Heidelberg, which is one of the people who really started work. AI, asked me about AI, how AI is reshaping computational astrophysics. And to finish the talk, I think, again, I mentioned this already, but I believe we are at the stage of AGN astronomy, where we are finally connecting the phenomenology that we see in this rich AGN view that we have been observing for many, many decades to AGN physics, and we are tracing that the main parameters that dictate this rich diversity of the AGN view, not only orientation, but also accretion rate, but I think also speed and magnetic flux from jets. So this is a summary of my talk. Thank you very much.
Thank you. And for questions?
I want to ask you a question I asked Roger a few years ago. It wasn't able to answer. Very simple one. Why do
those are the worst questions. The simple ones are very
why do these big AGNs, in the sense of powerful, highly correlated, only exist in and on top of that, only a small fraction of giant all microsystems are the same.
I think the last part was stuck on the microphone, but I heard you. So Lewis is asking a very good question. Why do we see very powerful jets only from hosted in elliptical galaxies? And the second part was
only a small fraction of galaxies.
Only a small fraction of elliptical galaxies. Well, if Roger was able to answer, but my opinion is this is related to the boundary condition of gas that is reaching the aging in elliptical galaxies versus this galaxy. Okay? Because we know elliptical galaxies are different from this galaxies, capitals. But I really do believe it's the boundary condition, and I think that this kind of simulation, the outer boundary condition of the accretion history, and this was outside the theoretical possibilities of modeling until recently. Forget about testing this in cosmological simulation galaxy formation, because no, the agent is a cell in your simulation, and then these people mostly use speed robots, feedback people, theory people. Well, I have my theory as well. But you know, you still use the bounding accretion, since model accretion agent, learn to tell you something about the simulation. But with this work, I think we will be able to test this how the conditions of material from the elliptical galaxy connects to the boundary radius and beyond below the boundary radius with this kind of exciting work. So this is my idea.
Questions? Related to Luis' question. put on the idea of wire against isn't that the idea that's in the little galaxies we have less gas or fuse, and then the accretion mode is relatively inefficient. Yeah, you said this in the past that this would be better.
Yeah, no, we know that you need a puffed ride, like a very hot puff accretion is usually low accretion rate. By low, I mean low Eddington rates below 1% of Eddington. But the important point here is why you get riots to begin with in the elliptical galaxies versus other types of galaxies. And I believe it's due to the low angular momentum of the gas to begin with. Like when it's fed into the boundary radius, it already comes with low angular momentum. And then somehow you get a riot. Okay, but nobody has actually done this carefully, like taking realistic outer boundary conditions of the AGN and simulating this with what you expect from the galaxy. And this was done for Sagittarius A star. Okay, this was really impressive simulation with Sean Ratzler. So what you're seeing here is a simulation from horizon scales to what do you know, parsec scales, but still this is impressive. And what Sean did, what he did here, the boundary conditions of the black hole, he is self-consistently feeding the black hole with mass loss from both Friday stars that we observe in the galactic center. We need to do this for actual AGN, not only Sagittarius A star. And I think this is the first starting point.
One last question, please.
Thanks, Rodrigo. Fantastic talk. I just want to go back to the point of spin parameter simulation. So what are your expectations, and are there any works that are trying to simulate AFI, which basically supposed to try to get the spin parameter based on biaxial limits, right? And so there's a lot of eager by Kristen also points to that fact that a high spin parameter is sort of a 10x equation to get the black masses oscillation. Yeah. So are you aware of or any comment that you might make on the way of cases, and how is this transition happening, and what exact parameter space are we talking about when we talk about this thing?
I didn't really understand part of your question, so what is the question about measuring magnetic flux?
Basically, the estimation of spin parameter comes down to the alpha estimation.
Oh, yes, okay, so it's not only K off, but the reflection signature of gas. Okay, so you're asking why there is a selection effect towards rate by AGN in the speed and motion. Yeah, I think it's because these methods they rely on having dense optical thick material where they are offering a reflection surface for continuum. And then you see the reflection surface on this gas close to the strong field regime of gravity. And so basically by construction, you have a method that is excluding radial AGNs, because radial AGNs, basically you have a lower density gas in this Rayet accretion structure near the black hole. So having the reflection signature is basically excluding most of the radial population. So one thing would be to make a proposal for trying to get reflection signatures in radial AGNs which have very high accretion rates, where you hope to have like an optically thick disk launched in the jet. So if you are writing proposals, actually proposals, think about it.
Okay, thank you, Rodrigo. This second question. Page 6. The next talk by James Leftley. Thank you very much. Thank you so much for talking about racing sound formation, projecting induced turbulence. Thank you.
Thank you very much. That's awesome. I'm going to talk about the activities and about how to do next operations for the Galaxies. So I want to talk about feedback. So we've had a lot of stuff about feedback already. And suffice to say, there's a lot of different ways in which you can transfer energy from the platform back up to large scale galaxy and therefore influence our galaxies all from star formation. But it's also a rather complicated issue, as you see, we're making great progress. So it's very hard to find a consistent way in which to have on phenomena and results in self-forming star formation. But there is one class of objects that actually does have this consistent signature, and that's modex or level hydrogen emission. These are all radio galaxies with radio AGN. They all have very low rates of star formation, and they seem to have very strong level hydrogen. And this is quite important because when you compare them on the chemistry relationship, the relationship just of the amount of gas that is being stars versus the amount of stars that are moving. You get this black line, which is what it says to be on the galaxy. And all these little triangles will get the modex, which will use one of magnitude below this relationship. And the level hydrogen is quite interesting because the type of blue, especially when it's strong, it traces 100 carbon warm gas. Not dependent on the stuff used for stars. So this suggests that the gases that these galaxies are quite warm. And not only that, the line ratios in level hydrogen seem to be used for the specific shots and rather broad. So the idea is that you have a jet coming from the radio AGN, it's driving the surrounding galaxy, it's making a shot front, heating things up, and it is and there's a galaxy forming stars. The thing is, this is being done on relatively unresolved data, either just from unresolved measurements, spectra, or from relatively resolution reasons. So what we want to do is really what's going on. To do that, we have a look at one such object, 3C326. Now, this is one of the most well-studied objects. It has this very strong molecular hydrogen emission. It has this very low star formation rate. And what's quite important is the AGN is quite weak, these relatively speaking. So it shouldn't be photoionization, that's the main cause of hydrogen emission specific. It has unresolved spectra, and that unresolved spectra, just when you look at Galaxies, says that license shots, and they're right above. And it does have resolved IFU studies specifically. Relatively low resolution, but still you can resolve the galaxy like this. So you have this nice local hydrogen emission that looks great as a norm. And you have a location which very much like this. But the issue with this data is we can only say that the gas is shot on the whole factor scale. And we can only say that we don't really see anything that's super much of a shot. Given this going to be this. So we want to get some JWST data for this. The JWST is what comes down to resolution symphony, and that can give you a very broad and solid view of that same molecular gaseous structure. So you can see symphony here and the same position that we have with JWST now. So what we want to try to find out is if the morphology of the molecular gas also shots in that way, whether we can detect this turbulence down to small scales. This is important because turbulence has to be in small enough scales to construct star formation. If it's on just large scale, you can still have star forming concepts. And you also get some JBLA data as well as some carbon data. So we can study the radio structure and also get a measurement of whole gases. scale. So we've got covering the entire 2 to something like. And this is an incredibly rich data set, and quite about being organized. I just wanted to say because there's a lot going on. And we have definitely not done everything that's possible with data sets, we have at least 90 operational lines, 3 rotational lines, a few IOs ones, continually with times to get the as well as banks, which is quite important, because this allows us to get the zeros, the zero velocity, the systemic velocity of the galaxy. This is because Zihuagn is the systemic one, so you can get a systemic pressure about velocities in the galaxy. So just fit a Zihuagn template spatially resolved to this galaxy, you get a very well-defined pressure. We find there's basically no limitation in some components. This is expected, this is a very massive galaxy, so much data. So we have a pretty good zero for our studies. But then to all of the hydrogen emission as well as ion science, we just go ahead and create a simple 1 or 2 Gaussian model. I'm not going to go too much into the fitting process, but it's pretty standard variation efficiency fitting activity. The other variation things we have non-uniform differential velocity primes, and I have to talk about that. But what we find is that all the line profiles we get across the whole galaxy are quite complex. They're at least 2 components. They're all quite hard. So that turbulence is there, and this is indeed going down to the smallest scale species that it will. And if we take the molecular gas lines, especially the rotation lines, and work out how much hydrogen we have in this galaxy, we find that we have quite a lot of warm gas, very stable gas. In fact, when we look at the CO data, we can actually detect any CO. So we, despite the fact that these are relatively deep observations, we just don't have a CO emissions from political gases. So we have at least 3 times as much warm gas as gases. So it's quite safe to say that this warm turbulent gas probably wasn't better starting emissions. And what's causing this turbulence in nature is quite related with energy markets technologies. So I was quite surprised with one more case because when we look at the synchrony data, it's this too special. When we look at the continuum, we see a nice order regulated. Okay, but as soon as you go to all of the lines except for one of the line response, you see not just this molecular gas disk, but it's a cavity that is being formed inside of this. And so what this is a bubble that is being inflated into this that has a shell of shocked gas that is currently fragmented. This shell has a temperature differential process. You can see here in the 0,0 line, you're more on the left-hand side. In 1,0 lines, which is warm gas, so you're more angry. And then the ionized transition now we work like this. So there's clearly a temperature differential across the system. And as well, also seems to contain quite a lot of very hot gas. And when we take a look at radio data, we only actually detect this unresolved radio core that's in this white contours you see here. But if we integrate the radio for the whole galaxy, what we find is that somewhere between this unresolved core and the entire galaxy, half of our radio flux is missing. This is actually what we expect from playing massive emissions of such objects. And basically what we think is happening is the radio jet is launched in the central region. It hits like a dense clump of gas and starts forming up. This generates an awful lot of radio plasma, which is going to inflate this bubble. And this radio plasma is too low surface quite distant in a resolved manner, but it still contains quite a lot of energy. So we can say with confidence that this seems like a jet inflated bubble where inside the molecular gas disk. So this is most likely what's considered very warm in the subject and very turbulent. And this was backed up by a coincidental paper in Unveiling. And this was a nice work that took about 60 days to work. And fixed more advanced shock models and focus association models to the detected molecular hydrogen transitions. And they used this prediction to predict the frequency of J-OST. So the surface of what they predicted, you can see by nature of shocks and association, and the stars are what we get. So you see that this prediction was extremely accurate. So suffice to say that this is very consistent with shocked gas mixed in with photographic association. So if we take a step back and we then go up and compare this, our star formation rate to the amount of gas we have for relationship, we find repeat like this is one for slightly far below. Now, if we're very concerned and we only use the CO, what we find is that using our argument, giving forward our this would be less if that is far below that value. It's not limit, but with the negative 20 times below. However, if you use the molecular gas detector, which is the majority of the warm gas, which is the majority of gas in the subject, you fall over 100 so then they will start on galaxy. So we can say in this subject, which backs up the fact that in the other ones as well, we are using jet-induced turbulence to see the suppressing star formation rate in these galaxies. So what we want to do now is go a little bit of a larger sample, but not just on the Wojtowicz. Because Wojtowicz are an extreme example, and ones where the shots are so strong that it produces incredibly strong. But we expect this feedback to be just as well for very low objects. We saw something yesterday that is being a possibility. So we're building a sample of such objects, and so far we seem to be showing we have the time I'll show you a bunch of images of that. But I just wanted to include this extra bonus bit of information that we just did, because we have quite a lot of thoughts about hydrogen. The selected hydrogen, as we see here, is a fantastic tracer agent feedback, really important. Something's going on, like a shot, whether it's a condensation, and that gas is being warmed up to the stars. But most of the time, a bit of a generalization, if you study the rotational, it's not necessarily rotations, because the rotational lines are short wavelengths, so you have higher resolutions and directions, but they're also expected to trace much more gas. So if you just want to check enough objects, what happens if you try to use these to provide gas masses and properties that we are using our rotational lines to connect in this one object. And we find that almost identical to what changes a little bit is the amplitudes. So if you wanted to use them to get masses by the amount of flux, you would have a bit of an effect depending on the different regions. You find different ratios between regions. But this difference is not that big, it's 60%, which is less than the assumption on a conversion factor between flux and mass. So you could do it at high redshift as long as you are aware there is this increase in certainty. So this is my summary, but I have a couple of minutes there. Then I will just very quickly show you.
You have questions.
Okay, well, instead, you can just see this picture, which is a very good picture. So I don't know if I'm particularly I'm not well known, but it's a galaxy. It's given really based on the high opportunity, based on the radiation, course of the Kimby series again, and currently we might say a big visualization is based. So that's thank you very much.
Thank you. Anyone questions? Okay, thanks for the talk. Just a question. It's on the slide. It's a kilowatt per second level. So you see this is
enough to sort of drive the suppression of star formation species.
Yeah, basically everywhere we detect selectable hydrogens in this object, leading transitions on
Yes.
So we saw you're right, that Galaxy talked about yesterday. So how do you think that these two situations compare and contrast?
Do you have which sense that can be?
So 4258 has the structures that the shocks are being produced locally.
Yes.
So and that's creating the radio structure. Like you're saying that the radio structure is going out and expanding outward at the bubble of the plasma and then creating shocks. So how do you think those two environments compare and contrast that we're seeing potentially similar instances?
I think it's a very similar situation. This is slightly like balance. This is the radio plasma in the first place is generated from shock interaction with injected power, which then reduces the plasma, which makes this large bubble. But I think it's shown that in this object here, which is much more local, we also have these bubbles being produced, and there's just a much lower power jet, so they have a whole balance.
Yeah, and then I cathode photon names.
Yes, so in this object, in every transition you see shocks except one element, neon free, which looks like that.
Well, thank you very much. Let's thank our speaker. Thank you. Next, we have a talk from Wojtowicz. Hello, thank you. So first of all, I would like to thank the organizer for making the opportunity to present my research and the network with the collaborators who are listed here. My name is Anna Wojtowicz, I'm currently in the Loudness University. And today I will be talking about the regular atmosphere between Galaxies and low planes. So let's start from giving you a little bit of the historical context and motivation behind this research. So it doesn't need to be introduced to this audience. The radio galaxies can be divided into compact sources where the emission space will be mostly associated with cell vision and extended sources. So at the end, in the last century, Tellerman proposed way to classify the galaxies using the ratio of the radio luminosity and 5 compares to the E-band magnitude of 4,040 Armstrong. And this ratio was introduced to classify quasars, and since then was not studied in many papers and is believed to be well established, however, still the data class sound the basic environment can be due to presence of the surveys or installations of products. But the data analysis of the lower accretion rates is not the well studied, so this is the reason why we started looking at this. So at the beginning of this century, in 2008 and to extend the sample of regular values by studying resources with the information down to 10 to minus 6. And they found that there were those two nice branches which they didn't really believe they existed. This can be because they selected objects in such a way as are super galaxies, and here we have grand around galaxies. And there is this clear trend, and I divided this into the three regions where here you have Blazars, here you have intermediate sources, and here you have really low different sources. Later it was again, what happened to the study of machinery in 2020, and it's uniform selected because they used sweet blood AGNs, and they found that distinctly two samples with a separation. Here we have compact sources, and those are sources with vertical logic. Of course, all of the samples were limited to the very low number of objects and relatively to have as much as possible. So our network chose was using 0.2 cameras.
which was created using SPSS database made by sample and was sample, so this was given to AGNs. And the pattern was created by matching SPSS maps with NPSS transfers catalogs, and each object was classified and found across identified optical cost identification and morphology was fulfilled by 10 factors, so this is really satisfying approach. The advantage of this catalog is that Starlight is that in 2005, Sigma Hernandez did all of the spectrum with Starlight, and thus we already have spectrum spectrum masses, mining velocities, and spectrum estimated using this spectral synthesis code. So having a diverse sample we have, we are using some diagnostic diagram to classify our sources. So this is the scheme which we use to deliver our final sample. So first of all, we look at the DLM diagram, which I present here, and we divide and set that each source is above this line, then we various attributes associated with the AGN emission and without also named outside formation rate. Then if rate was dominated by AGN, we look at the everyone with H alpha line, and if everyone equals to 3, then we say that the source was inactive and we call it obvious. So the rate paralysis without emissions line. And for the optical active sources, we use PPT diagram, and if the position of the diagram indicate the presence of AGN, we keep those sources that we upwards. So rate paralysis with emissions line. And for the secret, we created the catalog of secret paralysis looking at the sources where rate emissions will be dominated by cell formation rate. But the PPT diagram position indicated there is some AGN, and we remove the fake AGN accuracy equivalent with OEM. So at the end, we have three samples, each of them having about between 2,000 objects. So this is the large data set, and we slightly modified the definition of regular Loudness and the one was by other and because we had the only luminosity as one for pictures, so we assume spectral index of 0.8 to translate the regular luminosities to 35 gigahertz and luminosity to 1.4 gigahertz, and the scale is quite simple. So we assume also that 10% of the peak luminosity corresponds with the luminosity. Okay, so now we have another issue. So we have 1.4 gigahertz luminosity, and we know that star formation rate can contribute to this luminosity, especially in case of the secret galaxies. And in case of the coronal luminosity, we cannot always rely on the emissions lines, and even emissions lines are not different to estimate the coronal luminosity. Okay, so first, let's look at the star formation rate and how it contributes to 1.4 gigahertz. So, as I said, because we have star formation rate estimated with Starlight, we decided that we go with single scaling. So we use March 2011 scaling relation to calculate what is the expected 1.4 gigahertz luminosity, knowing star formation rates from Starlight. And then we just subtract, we found that AGN associated with the luminosity by subtracting from Okay, so now let's talk about the volumetric luminosity. So we have two cases, objects and secrets which have emissions and objects which don't have emissions. So let's start with this one. So in this case we use spin of Leo at 2024 scaling duration, which we have 12 micrometer. So here we use 5 because we have as many sources as possible, and we check how this relation works when we compare to model of the luminosities which we mentioned. So in case of the sources with emissions line, we receive oxygen-3 and relation we obtain representative paper precisions at 1.5. And here the volumetric luminosities, which you see here, were calculated using Loudness, synthesis code, and so the chemical organization code, and empirically motivated this, and we took into account the contribution to the emissions manifest from the region within the diagram. So you see that this correlation is very well, so we can use oxygen as its directed. So here I present our results. So here you can see 4 plots. Those plots are based on the emissions lines, and you can see that apparently there is no separation. We only could obtain separation if we manually remove sources. So we only include radius filters and extended optically active radio galaxies. However, removing sources manually. And if you look here, the prime values correspond to the by including the objects which are relative luminosity estimated on 12 micrometer. So you can see that there is large overlap between sources. Again, there is no separation, but there is large spread. And again, here we look at the morphological classification of the sources, and we see paragraphs associated receivers, but here, but again, there is no clear separation. So we have this large spread, especially in the case of objects, it was about 4 orders of magnitude, and in the case of spheres, it was maybe a mixed target tool. So we decided to use very simple, basically existing models. So here I present just the formula presented by Wojtowicz in 2011, which links jet power with the accretion rate and the magnetic flux and electron spin. Here the magnetic flux is expressed as a function, as a fraction of the total magnetic field allowed by the model. So we of course only have jet power, we don't have very luminosities, and there are various scale gradations which exist in the literature, but there are more consistencies which is presented here. As for the accretion flow, we can say that radiant efficiency is a fraction of the total luminosity to the mass accretion rate, and the problem here is that for lower, so the lower rates is that the radiant efficiency is not constant, but we need to scale more linearly with the mass accretion rate, so everything is function here. And from the definition of lambda, we can use this reason we can express the result as a function of the mass accretion rate. Then later with those 2 formulas, we obtain a super scale which allows us to, in a framework of the theoretical model, observe radio loudness and radio luminosity as a function of the observed parameters such as formative luminosity and the black holes, and this is the term which is unknown for this magnetic flux and black speed. So first we wanted to test what is the alpha value. So here we presented some lines. So if alpha was equal to 1, we see this version scaling scale, which is followed by cohorts and secret galaxies. So we say that we prefer using this value as the most likely one, and then the relation between the radio luminosity and the Eddington ratio becomes very simple, and it's just a function of Eddington ratio, especially at the lower it's a function of the lower Eddington ratio space, and the higher it becomes constant. This seems to be true when you look at this plot. And then there is this large spread, which results from the variation in the term t squared and the function of the electron speed. Here I reach my conclusion that we found that the distribution of radio loudness is smooth for galaxies at the lower accretion rates. We found no evidence of the prime value if we manually use some sources. The Loudness parameters is correlated with integration, and by applying targeting parameter with the parameters to the states, which allows us to regulate the luminosity and radio Loudness to performance in accretion related luminosity and the performance. The observed spread out of the order of magnitude of certain sectors can be contributed to variation in the diminished magnetic flux, but only the factor of 4. And assuming the critical spin is in what we call realistic range, so from 0.6 to 1. And thank you very much for your attention. We have time for questions.
Very nice. In a MUSE or I don't know, can you say how do you get the actual mass or force?
Yes, this is made on the velocity dispersion. But we have some solution consciousness, and for those is sort of I hope it's yeah, I focus on thousand using this because when you process can contribute as well. So actually I will not repeat mainly as questions.
I have a question. Do you consider generalizing your one in your samples? Because I'm also about your kinetic correlation that you mentioned within the ratio and the jet sources. What about the generalizing ones that you show with jets? They are very high in the ratio sources, so that's my question.
So we are using only type 2 agents.
Okay. So you are not considering them in the sample?
No,
It's just any other question? Okay, our next speaker is Miguel Coloma Puga. He's going to talk about the recalls during the central regions of type 1 AGN. Thank you.
Okay, can you guys hear me? Okay. So I want to apologize first thing because my talk is not really too focused on that, but we're going to be talking about something that's important in the study of compact gas, which is getting rid of the AGN pieces and studying the kinetic of the gas in the regions. So as you know, AGN feedback is a very necessary ingredient when we use simulations of galaxies. Because we have galaxies that are overmassive and undersized, we're not able to reduce the morphokinetic properties of galaxies. But the picture of how AGN feedback actually affects galaxies is not. We have evidence of circulation pressure, which is debated very strongly here. We have evidence of circulation enhancement. And if one wishes to, I think this is a very noble pursuit, to try to characterize feedback in single galaxies, with single epoch observations,
the state of the art method is to use feature flow observations because they allow us to simultaneously characterize not only the kinetics but also wire process and combine this with spatial results observation. And then again, the markets are different because they are these slightly unknown sources in that time again within the information scheme are supposed to be image processes. So the observation from the galaxy itself as well, we should be able to move to the central regions more clearly than time too. But the reality is we have a very bright pixel, which in many cases outshines the galaxy, and if not, it really can be contaminated in those galaxy spectrum. And so the question becomes, can we actually mitigate this? Well, the answer is yes. To do this, we use a process called equation light subtraction. To perform equation light subtraction, we need two linear extension ingredients. One of them is the P stuff of our observations. The second one is the AGN extension. The P stuff of observations is simple enough. We can use source in the field. If our AGN is right enough, we can use the AGN itself. And if all else fails, we actually model it. And what we did in my case is you start in the field and to get all of. But the AGN spectrum is a bit more complex. So let's call our AGN spectrum as stars, which is composed of the host lines, stars, glacier lines, and glacier routine. So total host of the glacier. And in really bright AGN, what one would usually do historically is to take the central pixel or the central pixels and use those as different. What that means is that you have a total loss of information in your region because your central pixel is going to be 0 and your centermost pixels are going to be 10 meters. So can we do better if the sort of information is up? Well, we can. So what we can do is use regions that are far enough away from your place to use your pure observation. Then we can look at the entire galaxy with a species match, for example, again, in the galaxy allows. And obtain what the solar spectrum should look like. Then we subtract this from the observed spectrum, and we should be left with pure generation. Now, this method is really nice because it works for both high and low luminosity, which can be used. And just with the iterations, we usually rely on fairly stable solutions. It has pros and has cons. So some of the pros, we have the potential to cover the entirety of the abstract emission down to the central pixel. And also, we have no dependence on stellar or AGN layers. So if you have really weird objects like this guy here, where if you can tell me what is going on around the top, I will give you the first offer and I will give you this. We have no dependence. It's purely data and information driven. Some of the costs is that we need many assumptions or conditions to actually hold the so we are slow properties in the nucleus and the outskirts, not necessarily very far away, around the AGN to be fairly similar. We need our slow model to be consistent throughout the galaxy. We can't have our surface index changing massively. And we need a small velocity field in order to not sort of artificially draw the lines. And so the first object which we apply this way on the HC628, also known as that thing, which is actually a more complicated thing, is a type 1 engineer, very nearby. It's formed by extremely abundant, just 7 years old, 2.5 projects projected size, and it is also a low power radiator. And if you look at HC imaging, it's hard to see, but it might be excused to think that this is a elliptical, particular galaxy, where in reality, this is a very nice spiral. This is not each. And so we go into light subtraction. So as I said, what we do, we take the AGN here, we take the whole in the center square, and we're going to model the galaxy around and subtract. And so on our first iteration, we can clearly see that this is a very low luminosity AGN. The observed spectrum, which is in the blue, already has very clear stellar features, and the green is very stellar as well. And we are left with draw lines from the AGN. And just narrow lines and subroutine for those lines. This is for first iteration. We can do another iteration, and you might easily again. This looks exactly the same iteration. And that's because on a log scale, if we go to linear scale, you can see that we are basically almost not just in iterations. So in 5 iterations for this object, we were completely finished. And now we can go to study the slow properties and the calculus. So the slow component, we've got the usual illustration, which is 188 and PSI. And we find thermal kinematics which are continuous, we have a gradient, we don't have any jumps. So we can be pretty sure that we have anything else in the students. If we could, and if we had enough spatial resolution, we could use this to estimate the black hole mass and then we from within the sphere frequency. That's how we use this cannot spatial result that close. And it's a job for the at least. And we observe sort of similar results in the sense that they are mostly constant because we have a more aged, more rich population towards the coast as compared to the outskirts. And so, as far as we're concerned, at least in the center, we are not affecting the solar properties of the center. Then we can go to the relief distance, which is the IMX test. So we follow a similar process. In this case, instead of PKS, we use analysis, and we optimize it based on the nice statistic. And to be honest, this might look pretty normal, just a galaxy rotating, but there's actually a little lot going on in the center. So if I zoom in, you can see that there's a counter-rotating disk here, which is completely perpendicular to the rotation of the galaxy. And so you might be wondering what this. So what this is that this has already been observed with molecular events, both with Alpha and with symphony, H2 and CO. So more than molecular gas. We have an inner disk which is about 650 parsecs. It's rotating completely perpendicular to the main rotation of the galaxy. And there's a really nice study by from 2014, 2016, and 2018, where they interpret this as ongoing feeding of a black hole, which is actually the cause of this young jet. And this is a really good litmus test for our subtraction because we can record very small standard kinematics in completed info observations. We can check our atomic clocks and find that it's actually quite similar to this vertical structure that we observed in CO, which I thought was quite interesting. And now here come the feedback questions. So is there an output here? We find that there's a broad component which is quite extended. We find that it's mostly two-sided. So we have the red emission here, the emission here, somewhat enhanced fluid enhancement in that direction. And we also observe it in O3. The working with the example is that because O3 is not extended enough, it's much better than the subject. So we decided that even though we deal with a lot of them, it was the better option. And we can overplot the excess of this proper component or the main flux. We can see that obviously the main flux still has a main impact, but we see this excess in that direction. And we can check the spectrum on these positions, and we see that we have sort of very low velocity, low dispersion velocity growth component, which should be interpreted as an output. Again, it's the question. So we can go to the BPT diagrams, for example, the SBPT, and we see that in a very similar direction, we have an enhanced liner emission, so lowest transformation, greatest liner. Again, this is the low velocity AGN, so we didn't really expect to observe pure AGN ionization. And this is more or less the schematic of what we think is going on in the subject. So we have the approaching jet, the receiving jet, which actually agrees with the fact that we observe more transformation information this side and this side, and also here's the velocities, so it's quite consistent. And just to talk about the jet, it's not the jet section. So this is classified as a GPSUSC zone. It was observed, which is very low baseline. And again, age of about 70 years by the separation between components. And as you can see, it's a bit of an output just based on the following. The hotspot is here based on the spectrum index, and we're actually not sure why it's sort of, it looks like it's circling around. It's a bit of a strange case. And so in our observations, it actually makes it possible to observe the effects of the current jet. This is just small, 2.5 parsecs per record size compared to the 60 parsec we use pixel scale at this resolution. And we think that this is a new cycle of activity based on the conclusion that this is the outwards. You know what it is. I believe personally that this is an object to look out for in a solicited feature where facilities like given currently should be able to resolve the jet in optical and even get close to resolving these sphere mechanisms black hole. And quick recommendations. So for Spanish for me, like Anima, it's as a trigger, it's kind of a hard push, but I don't even like Spanish signals, so it was difficult for me to choose. And then my actual recommendation is Loudness control, which I think is an absolutely essential standard for me.
and we're living a strange life, so it's really nice what's right now. And thank you.
Hi, that was a big talk. For when you are, let's say, one of the very famous AGNs, assuming that the contribution from the host disk is modeled as a fair way to this, how do you know that what's remaining is something really famous is a contribution from the AGN rather than a contribution from lumpiness in the disk or something else that wasn't properly captured in the disk attached?
You can. It's impossible. This is purely data driven. You have to sort of convince yourself that you're doing this right. And yeah, I know, but dealing with low models making, you probably know that it's very hard to model them. In a lot of cases, they don't follow the sort of common AGN libraries that you use with higher velocity. So you have to, in a sense, convince yourself that what you're seeing is real. And in our case, I mean, I was fairly convinced by the sense that the spectral wave service is basically raw lines and sort of white frames
right.
That part will contain. So besides this double peak here, which don't really know what's going on, everything that we observe goes with expectations.
Oh, thank you so much.
Okay.
I know what you're expecting that you showed. The first spectrum that you showed, you didn't know what it was.
Right. I prepared extra slides for this. Yeah, here we go. This one, right?
Yeah. This is a double peak channel.
That's what we thought. That's what we
think it's not because it's very similar.
Yeah.
That I have studied. Yeah.
It's very similar. So I have prepared the slide for this. So this is the double peak profile. This is a channel file. So if you take the centroid, it's actually over here, and more than that is the fact that you have the boosted side wedge, and you should highlight it.
I have seen it. I have seen.
You've seen it?
Because if you have a disturbance, this is like a this like major line, and if you have a disturbance like spiral, so it's actually very similar. You see that it's certain things also fine. And sometimes it shows the red is stronger, and maybe it's gravitational wedge. Maybe that it's all
it could be right, it could be, but when we go to H data, then we see nothing.
But you have some parameters. Always the data should be at least 1/3 of the power, right?
Yeah.
So I think no problem because it's not so strong. So if you take 1/3 of that, maybe consider it.
It could be, but also I will mention it's very rare. Here from 2017 to 2023 it appeared, and from 23 to 24 it disappeared entirely.
That makes sense, like you receive. Yeah, so it's something very effective in this solution.
Yeah, it's point line necessarily it was suggested that we know what it's like and usually this probably not a server.
Thanks, yeah. I was interested, I didn't quite know what everything we do there. You said that instead of using points per count, you were using a search profile. Yeah. Did you make an assumption about what kind of search profile? In other words, what number, or did you just leave it? Okay, and so we use that. Okay, and then basically it comes out. Does that also work? Does that work for nearby objects or
yeah, so not correct version, but this method is sort of creating an image of nearby object, which the right screen up with just 2 images of the device. Okay.
Okay, let's send our speaker and we work. Now we receive another. She will be the last call of the governance session.
Hi everyone, welcome to the very last talk of this conference. Thanks so much to the organizers for this amazing event. So coming back to jets, let me discuss a little bit of the relationship between the gamma ray emission and the radio emission in blazars. I am a PhD candidate at INAOE. This year are my advisors, Victor Patria, Michelle INAOE, also Sergio and Sergio and Giovanna, and be IFA. Okay, so let me start by mentioning two open questions that haven't been resolved within the topic of jets in blazars that were not mentioned during the review talk earlier today. So the first one is changing of fuel. So first one is we know is what we thought is happening in jets is that the gamma rays are produced by inverse quantum scattering, which means that we have these very energetic relativistic electrons that are going to give energy to low energy photons. So the question is where these low energy photons come from. And one of the possibilities is the cell synchrotron cell photon, which says that these photons are from the jet itself. So from the synchrotron low energy photons, the attraction to the radiation will gain energy and we will see them as gamma rays. The other possibility is that external inverse photon here. So this one, external means that the photons come from the external structures here, will be the version is the torus or the BLI. So we don't know this yet. Second question is, what is the blazar region? Where actually the gamma rays that we see from blazars are being produced? So, over the years, we have had many different works and results. Some of them point to gamma rays being emitted close to the black hole, so inside the BLI, this would mean that they are coming from the inner parsec. So from over here. Then we have the opposite idea, and those that say that they come from the outside the central parsec, downstream the jet. And more recent work mentioning that both cases can be happening at the same time. And what I think is happening here is not that these are wrong results, it's just that we now have more years of data. So we have a broader picture of what's going on here. So we have radio elements that come from the jet, others that come from the inner parsec, maybe. But I'm getting ahead of myself. That's kind of a conclusion. Okay, so what am I doing? I'm studying jets using the highest possible resolution, so intensity maps from the NBA. In particular, there are two amazing monitoring programs that take roughly monthly images from blazars and a few radio galaxies. These are windy at 43 gigahertz and Mojave at 50 gigahertz. Windy recently also started taking images at 86 gigahertz. So we have BNDI maps from a few tens of blazars starting since mid-2008. So we have over 18 years of data right now. And what I aim to do is to characterize the parsec schedule structure within these jets. So what I mean by structure is all these blobs of plasma that we see moving around here. I'm showing the jet. And an important ingredient here is that by using these two frequencies, we can map and study different scales. First one is that by looking at the 50 gigahertz Mojave maps, we can see somewhat the large scale of the jet, so few tens of parsecs. And we can characterize these structures in the jet. By looking at the 43 gigahertz minimax, what we can see is structures at smaller scales. So, for example, when we are looking at the 15 gigahertz core, this will be the gradient core. Once we are working for the gigahertz, what we can gain from it is to resolve smaller structures that we will be able to see at 15 gigahertz. So what do we do when we have tens of BLBI maps and a advice of the tens to feed all of those maps? That's my advice for offering me a PhD decision. And you develop code, right, to do it for you, so you don't have to keep repeating the same task over and over. So what we did was this automated batch processing tool that is going to do the bits for us. We designed this to work with the maps for the jets, but it can work with any intensity map. Yes, if you want to build a structure, it is very Casa, but it makes everything much faster. This one is a project led by Alfredo Matamontes, who will be here, but the code is already available. So, let me see. Second ingredient for this work is the actual data rates. Okay, so I am working also on some images that not the highest images, but AGNs. That important thing for me here is that we are using the maximum likelihood analysis around the object of interest with a radius of 15 degrees. But we are estimating gamma fluxes that are in time and center at the same level as the BLBI images. So we can use both line curves as was a simultaneous. Okay. So first object that I started using this method was 3C4 What we found is that we were able to characterize the O-levels of over 150 BLBI mass for 43 gigahertz and around 80 or 50 gigahertz. And once we have all these nodes, all these components characterized, meaning we have block positions, we have a position anchor also, we cross-identify and we are looking for these components that maybe be quasi-stationary, so we are looking for persistent objects with that. And once we have them, we can construct the light blocks. So, for example, the dark blue one here would be the core. Interesting thing that we see here is that usually Blazars are core dominated, but that is not always the case. For example, in this area here, we see that there is a node or a component that was brighter than the core. So we have to be careful how we define the core. Okay, so we have lighters for all these components, persistent components in time. And also, since we have positions, we can derive motion from them. Okay? So by simply assuming they move at a constant velocity, we have here the distance relative to the core at 43 gigahertz and at 15 gigahertz. So we can see how these components are going away from the core. At 43 gigahertz, we are tracing the smaller scales. You can see things happening faster. At 43 gigahertz, it seems more boring, but they are still moving. So, an interesting thing happening here is that we found these components that are being ejected from the core. And then they find this quasi-stationary component here, and then they disappear. And this was also reported in another paper. And one way to explain this, the disappearing nodes, is that the jet air is bent. So now it's pointed more towards the line of sight. So all the components are stacking there. Okay. So let's focus now and perform particular components. One is a mobile, one is a quasi-stationary one here, and then we have another two quasi-stationary components. So, what is the relationship between these two things? We're talking about radiation with components in jet, and also gamma rays. What we are going to do is perform correlation between the two types. The light comes for each component, and also the gamma ray total flux. And here, for example, I have this is the gamma ray light core, and here I have total flux, but also the light core in green for the core, and 43 gigahertz. And we can already see some coincidences. So flame that happens in gamma may happen also in the core, or maybe in another component. So that's the kind of thing I'm looking for. So the core of 15 and 43 gigahertz is closely related to the gamma ray emission, and this is what is expected usually. So we found correlations, positive correlations between the gamma ray emission and the 15 and 42 gigahertz core, which imply that around 27% of the gamma ray emission might be correlated or might be associated with the core. So we would say that almost 30% of the gamma ray emission comes from during this time period. And then we have almost 40% of the gamma ray emission comes from the core at 15 gigahertz. Now maybe you should say this is not something that's really why one core has more emission in gamma rays. And a possible explanation is that since the 15 gigahertz core is tracing or mapping a larger region, we have more than one gamma ray emitters there. Regions emitting gamma rays. Then we have also the case of the Q21 quasi-stationary component. This one can also be associated to gamma ray emission. What am I doing? No. Okay. Why am I calling this quasi-stationary? Because the frontal motions are consistent with 0. This one is at a little bit over 4 parsecs projected distance from the core. And 20% of the gamma ray emission between 2016 and 2017 can be associated with this particular region. And this one is, 4 parsecs from the core. But then another one, which is a bit counterintuitive, is this one. We have Q3, a moving component that is associated with gamma ray emission. Why am I saying this is weird? Is because when these nodes are moving away from the core, they are losing energy, so we will expect them to move. However, we see one that is moving and is probably emitting gamma rays. So this one is moving at around 10 times the speed of light, and we can say that 28% of the gamma rays are coming from this node. Then also we have the anti-correlations, the obvious cases. So here we have two components at 15 gigahertz showing the correlation between the gamma ray emission and the radio emission. But there weird things happening here. We explain this as possible gamma ray absorption, but we have very few points. Here, 11, which is the very to perform correlation, and also, at least for the case of K6, this one is very close to the core, almost at the resolution limit, so this may not be true. And then we have a second object, these are preliminary results, PKS 1510-089. So far, what we have is we have characterized the structure of this jet. We have one quasi-stationary component and one 0.4 milliseconds, which is this here. We have many moving components, and this object is like a very nice story. We see the gamma ray light core and also optical near infrared light cores, we see that many of these layers have a counterpart in the different bands, but also can be associated with a node that has been ejected to the moment when it was ejected or when it crossed the stationary component. So this association points towards electronic processes for the emission of gamma rays. Some pairs that we know so far for this object is that the 40 years again shows a correlation with gamma ray emission. However, the 15 gigahertz score is not correlated with gamma rays. So, my conclusion is that these gamma ray flares can occur during the increase in the flux in the 40 gigahertz PLDI core for both objects. This points towards the external effects component as a dominant mechanism for the gamma ray emission. So we are pointing towards one of the possibilities. But then we also have high energy emission happening beyond the core. So a few parsecs and even a few tens of parsecs from the core. So this fact strongly suggests semi-synchrotron component as the primary mechanism for gamma production. So this is what I was telling before, that we have both mechanisms happening at the same time in the same object. So this points towards wanting here kind of strong centers that some models, to some models for the gamma radiation may not be enough. And also, just to mention that we are about to start doing large number statistics, so few tens of blazars, and we are going to analyze them following the methodology and see what we can learn. If it is common to have nodes, moving nodes that are in the gamma rays, so it's very specific to let's see what happens. And those are my components and the gamma rays. At this point, you know this is my new implementation. Accretion, you can see it on your flight back home. According to the formula Oregonian, this is something sharp. So, yeah, that's it.
Questions? Maybe some. Okay, what can you show us? The line curves, I'm not sure if there is a correlation on the gamma ray line curve with the radial line curve. Maybe in the case of 3C 454.3. Well, in this case also. This one, for example.
Here I am not showing the radial line curves. Here I just have gamma, and optical.
So how do you establish the correlation?
Oh, I don't before I was showing one figure. Yeah, but I have the line curve for the core. I'm just not showing the position. But is what I'm showing here, for example, for the positive correlations that are statistical significant, I have a flux gamma ray over here and 40 years already.
Okay, but it is interesting because when you have variability, it always is like a, don't say that, but always when you lax, it's completely not coupled gamma rays. That's why you see from your results.
Yeah, the thing is that here has the statistically significant correlations. Some of them, this I would call it strong, but we do have strong correlations also. Let's see. 1 is 4, So what we are seeing here is this, right? Really strong correlations here. They are not linear. They are simultaneous. Okay. What's spatial?
Okay. Co-spatial, more or less co-spatial. And related, these two objects are flat spectrum radio quasars.
Yeah.
Why don't you observe or look for the same in the
Oh, we are doing that.
Okay, so it's future plans.
It's in the process.
Thank you. Well, let's thank everyone. We proceed with the concluding remarks. We invite. Omar says wait.
Because there is coffee in the bar, I think it's time for coffee, but before that, so we are going to stop like 15 minutes before the concluding remarks to have a bit coffee. But before that, because we would like to send